All right, we see Oliver's back. And now Oliver actually also has a relative. This here is Olivia. And they've got a little baby sibling. This is Ollie. And they also have a mom, Olivette. Kind of hard running out names. What are you doing? Giraffe relations. See, and they're a family, and really, they just function as a family.
Tibbs, this is math. Like, you can't just go around crossing out graphs and writing giraffes instead. That's just not how it works.
But they function as a related unit, just like it's related to this unit. Fine, but I'm still keeping them. I'm just shrinking them.
You don't want to do that.
I don't want to do that.
You don't want to.
Oh.
Perfect. Nailed it. So we've seen a variety of relations. Some involve whole values and some don't. So sometimes we have graphs with distinct points, and for others just like a single line or curve. So we can have two different kinds of data. Let's see what's under some of these hoops here, shall we? So discrete data. Oh, there's words under here. Yeah. Can I get it? Oh, nuts. I got this.
It's can. It's only data that can.
So close.
Just right
data that can only take on. There we go. Values in increments, such as integers. There's always a next value. So between there's not necessarily a value between every single two values. So integers are a case of that. There's always a next number to integers. What's after 2? Well, that's 3. What's after 10? Well, that's 11.
Oh, kind of like money.
Yeah.
Right? You could have like $20, but you could have the next increment would be $20.01. Yeah. Or $20.02. But we can't have $20 in like 0.000784962 cents.
Yeah.
No one has a coin for that.
Yeah. So even though dollar values aren't integers, there's always a distinct next possible value that we're playing with. But there's not always in between values. So that's discrete data. With continuous data, we're talking about data for which there always exists a value between any two other values. And that's for both the domain and the range. So the set in the domain needs to be continuous, and the set in the range needs to be continuous as well. If either of those is discrete, then we're going to consider the whole relation to be discrete.
So like continuous data, that could be something like time, right? We don't just go from 1 second to 2 seconds. We can have any sort of combination of like milliseconds, right? Or decimals. Same thing with height, right? I can be a meter tall. I could be maybe not 2 meters tall, 1.5 meters tall, but I could also be any value in between that, right? I don't have to be 1 or 1.5. I could be 1.0876259347823333336 meters tall.
That's pretty precise. But the point stands that if you think of a value that can be part of that data, consider if there can be a next value, or if you think of a value that would be the next value in your head, ask yourself, is it possible to have a value in between those? Is it possible to have a value in between 185 centimeters and 186 centimeters? Well, sure, there can be. And that's what we're going to be kind of after as we label these relations as having either discrete or continuous data.
So here we are looking at 6.6a, which is the number of tickets sold versus gross revenue. Now, when we're selling tickets, we are not selling portions of tickets. We are selling 1, 2, 3, 4, 5, 6, 7, 8, 9, or so on, right? We are not going to be selling, some fraction of a ticket because it would actually void the value of the ticket itself. So here, since tickets have to be in whole values and they can't be continuous in nature, it doesn't even matter what the gross revenue is. we can already label this data set as discrete. Although we can also look at the gross revenue and also say that that would be discrete, because even though we can have decimals in terms of money, like we could have $10.50, $10.5, we can't have any decimal we want. So there's always going to be an increment. So therefore, these guys are discrete.
We've got a projectile's altitude versus time. So projectile, I've thrown something or it's flying through the air. And we're talking about how high it is in the air over time. As a general default, time tends to be continuous. That's something that Ms. T said as we were talking about continuous data. And then altitude, that's a measurement of really length or distance. And that's just as Ms. T was saying, you could have decimals upon decimals. You could say something is maybe a meter in the air, maybe it's 2 meters in the air, but somehow has to get from one point to the other. So it's got to hit all the in-betweens. It can't just warp from here to here.
Man, but if it could, how cool would that be?
It's got to get to that point first. But in order to get to that point, it has to get to this point. In order to get to that point, it has to get to this point in between, and in between, and in between. So there's always in-between values the whole way through. So this whole thing, we could certainly say, is continuous.
At this point, we have 3 more examples. We'd like you to pause the video and try them on your own. And welcome back. So we are going to do the next 3 examples together. C talks about the number of shots taken versus points scored. So I'm assuming this is in basketball, or I guess it could be hockey, or it could be soccer, or...
It's definitely not the greatest sport ever.
It's not badminton.
No.
But here we have it. How many shots can be taken? Well, I can shoot on goal once. In that case, I guess I'm referring to probably soccer or hockey or something. I could shoot twice. I could shoot 3 times even. And I might get 1 point for it, depending what sport we're playing. I might get 2 points for it. I might get 3 points for it. But I'm not going to get any decimal I want of points or any decimal I want of shots. Those are discrete whole number values. So for those reasons, this is going to be discrete. In this case, both of our data sets in the relation are discrete. So this whole relation would be discrete as well.
A substance's mass versus its volume, that probably relates to density somehow. And again, we can't just jump from one mass to another. It's not like I was born at 3 kilos and all of a sudden I became the hulking 48-ish kilos I am today. I don't know what the actual value is. It's probably in that range. Anyways, I had to hit in between points there. So, and that goes for any bit of matter. It doesn't just suddenly, poof, disappear. So this is continuous.
All right. And this last example, a television's volume setting versus decibel outputs. Although I probably am not alone in wishing that I can have some continuous range of volume. If I'm watching TV or things like that, if I am clicking my remote, I am not going to be able to get every single decimal between volume 6 and volume 7.
But what if I am controlling the volume with like a dial on an amplifier and it moves really, really smoothly, like it's a smooth moving dial?
No, there's still going to be jumps in between them.
Shame. I'm returning that amp.
Yeah, so with a volume setting, I'm going to always have to set it at some point. Even with the dial, if you listen really closely, sometimes you could hear like the click between the movement of the dials because those are at integer settings to tell us what that decibel output will be. So since the setting itself is discrete, this whole relation would be discrete as well. Now, we can display discrete and continuous data on a graph, and since I was the one, for some reason, who did A, C, and E, and all of those values were discrete, I'm just going to show you the discrete data on a graph. In this case, discrete data will generally be shown as distinct points. So on a graph, I might see points like this, maybe some in the negative range, maybe some way up here. But I'm going to see these distinct points. They're not going to be connected, but just on their own.
And of course, since I took examples B and D, which were continuous, I'll show you what continuous data looks like. Essentially, you're not taking your pencil or pen off the paper. And when you start graphing from one point, you just keep going to all these other points. Wherever they go up, they go down. I actually don't really like that much, to be honest. But
kind of reminds me of a ghost.
Ooh. But we don't have distinct points. We have something that is continuous. It's continually drawn without any breaks in the chain here or there or anywhere.
Cool. So now what we're going to do is we're going to be talking about how to tell if a relation shown on a graph is discrete or continuous, but also how to tell if that's a function. Right? In previous lessons, we learned that something is a function if no element in the domain corresponds with more than one element in the range. Well, that sounds nice and all, but how do we put that into practice? We can actually look at something called the vertical line test. And the vertical line test is a method to determine if a relation is a function. That's its sole purpose. If a vertical line can be drawn such that it meets the relations graph more than once. So if I draw a vertical line anywhere on my graph and I touch that graph in more than one location, then that relation is not considered to be a function. But if I draw a vertical line anywhere on that graph and I always only touch it at one point max at any time, then it would be considered a function. So a vertical line test is a really great way to do that very quickly. Now, before we look at that, what I'd like you to do is really quickly just see if you can pick out which data is really obviously discrete and which data is very obviously continuous.
So we're going to tell if each one of these is a function. I'm going to start with this one right here. And in doing this, what I essentially want to do is take a vertical line, and I'm going to drag this across my function. And I'm going to see, my relation. I'm going to see if it's a function. I'm going to see if it ever touches the relation more than once. So like over here, for example, it's only touching the relation once. And I just need to make sure that happens the whole way through. So still once. In fact, no matter where I put this line, it's always touching that relation once. Just once there, once here. No matter where I draw a vertical line, it's always just touching it once. So by that logic, I can say that this is a function. I don't need all the words. It's a function because it passes the vertical line test.
All right, taking a look at this next one, we're still going to draw that vertical line. And as we take that vertical line and we drag it across our possible function, we're going to make sure it's only ever touching that relation once. And that's true as I'm dragging it along. I'm only hitting it once. Now I'm not hitting it at all. But only once, every single point throughout. Whether I'm drawing that line here, or here, or here. At any given point, it's passing that vertical line test. So this, in fact, would also be a function because it also passes the vertical line test. I'm going to put VLT just for this lesson so that we don't have to write vertical line test every single time.
I'm going to draw a vertical line. Oops.
Ooh.
Vertical line. Oh, so close. Vertical line. Counting it. That's a good one. I'm going to take that vertical line. I'm going to drag it across. It's hitting nothing, nothing, nothing. Boop! It's got a 1 in there. And then, whoa!
Whoa!
Whoa! Hey! Whoa! This is hitting this relation twice. Right there. And right there. Double whammy. So, that's a hard no. This is not a function. It fails the vertical line test. I tried to write it quickly, and I just ruined everything. I'm just going to write the vertical line test.
Okay, so something to keep in mind. Remember in previous units we said something is a function if every element of the domain only corresponds with one element of the range. When we're graphing, our domain's always expressed on our x-axis, and our range is always on our y-axis. So if we're looking at our domain, maybe the line that Mr. A drew, oh, that scale is not consistent, but maybe the line Mr. A drew is at the -2, when x is -2. So we could have maybe the point of, I don't know, this one here, which is -2, -2. X value is -2 and its y value is -2. And maybe it's -2, 3 for this point here. Well, notice that, that was much larger than anticipated. My domain, -2, is corresponding with more than one value in my range. It's corresponding with -2 and +3. So even though the vertical line test doesn't necessarily specify those exact points, we can see that if there is a vertical line that hits the relation more than once, it must correspond with more than one element in the range. So that's what the vertical line test is telling us, just kind of in a little bit of a simplified way. At this point, I'd like you to try the next few on your own, and by few I mean 6. And when you've done so, prepare to go over them. We're going to go through these a little bit faster. We have a vertical line here that I just erased by mistake. I'm dragging it across. Tra-la-la-la-la. Only hitting once. Hey! So this, in fact, would be a function as it passes my vertical line test. Woot, woot, woot. Boop.
Let's check out this one. There's my vertical line. I'm going to drag it across. See, this is a function. It's on, it's off, 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 it's on. But it only is ever on one point at any given time. I think we've got ourselves a pass.
Woot, woot.
We put the fun in function.
All right, this next one, just as a quick reminder when we're looking at things, when we have an open circle, that means it's all of the values up to that point, but not including that point. So we're not including the point exactly at 0 here, but we're including like 0.00001 or a negative 0.02. So we're getting really close to them, but not at all. Whereas if we have the solid point, that means we're also including that point. Just in case you are wondering, I don't remember open and closed circles. Hopefully now you do. So I've drawn my vertical line. I'm again dragging it across my relation. Possible function. Here we go. Hitting. Stop. Hitting. So at any given point, when I drag my vertical line across, it only touched that relation now function once. Or not at all. Function. It passed the vertical line test. Wow. Ooh, discrete data.
Check it out now. Ooh, I need to pick a color. This color will do. Bra! That's straight enough. So, whoop, we only hit once. Whoop, we only hit once. Whoop, we hit twice. Ah! Really thought I had more time. So, big nope there and there. hitting twice, so this is not a function. And that's so sad.
So even though it doesn't, or it passes the vertical line test earlier, it's still not a function as long as it doesn't pass in one location?
Yeah, so this is okay, but right here we've got a recycled x value.
Ugh.
We have an x value that goes with 2 y values. And in fact, we have it happen later too, but that's irrelevant because we've already established over here that it's not a function.
All right, this next one. Oh, what color haven't we used? I don't think we've used this one. Ugh, that's not really straight. Close enough. So we are going to move across this relation possible function, and we've got it. Only once. What's going on here?
What's going on over there?
Well, we noticed that it's hitting this point for sure, because that is a closed-in circle. It's also hitting this open circle. But as we recall from our conversation a couple seconds ago, an open circle means that it's not included. So even though it appears like it's hitting at 2 points, it includes the closed-in point, but then excludes the open circle. So it's actually only hitting in one location at this particular x value. So that's still okay. And we keep on going, tra-la-la-la-la, and it's only once as well. So this, in fact, would represent a function because it passed, or passes, the vertical line test.
And this last one. Oh, this one looks pretty radical. And if you don't get that joke quite yet, despite the only other time we've made jokes that involve the word radical, go back to this video in like a couple years. It'll be hilarious.
This is a graph of a radical function.
Spoilers! So anyways, yep, we hit once, and just once. In fact, if I scroll through this whole thing, we only ever hit this relation once. So I'm calling it now. This thing is a function.
Sweet. So if we look at the bottom of the page, once you've written down that this in fact passes the vertical line test and therefore is considered to be a function, we can see that there's some practice work. Give that a go. You can do it. Make Oliver and his family of relatives and functioning relatives, I suppose. Except we doofed some. So some limited functioning relatives of Oliver proud and get her done.
As the giraffes say,